Hello boys and girls, and welcome back to Rock the JVM. I'm Daniel, and in this video I'm going to demonstrate a technique for implementing data structures with forward declarations using call by name and lazy values. And the example that I'm going to use here is a doubly-linked list in Scala. Now, this video will assume that you know call by name and lazy values. I have a bunch of videos here on the Rock the JVM channel that will address both. And as always, I'll recommend that you code with me because this technique is pretty interesting and you might want to use this in other data structures or in other libraries that you might want to use in your day-to-day. And whenever you need to refresh your memory about this concept, just refer back to this video or to the article at the blog with the link in the description. So with that said, let's get back to our code. I just created a simple object that I called Doubly-Linked List Playground. I'm using a Scala 3 project here, but you can also use Scala 2. The code will work just as fine. So this video was inspired by a question from one of my students who understood the point of the initial singly linked list exercise that I usually show in the Scala Essentials course over at Rock the JVM, and wanted to move one level up and try their own data structures. So he picked a doubly linked list for this exercise, but he had no idea how difficult this actually is to practice. So in this video, I'm going to show you how you can implement your own doubly linked list with a technique known as forward reference. Now, a doubly linked list doesn't really offer too much benefit in Scala, quite the contrary, because the complexity is still big O of 1 for accessing the head or the current pointer of the doubly linked list. But it is still big O of n for basically everything else. So the complexity for a doubly linked list is pretty big, and performance-wise, a doubly linked list is not your first choice, probably. But the only utility in having a doubly linked list is the ability to traverse the list in both directions. All that said, a doubly linked list is a very, very good exercise on the mental model of immutable data structures, which we are going to practice in this video. Now, let me first show you what the challenge is with a doubly linked list by comparing it with a singly linked list, which is relatively easy. So I start with a trait that I call myList, and I make it covariant so that we can have the proper substitution there. And the elementary methods would be something like head, which returns a t, a tail, which returns a myList t, and a method to prepend or append to this list. I'm going to use prepend, and this takes an element of type t, and this returns a myList t. However, we get the very common but very cryptic error covariant type t occurs in contravariant position in type t of value element, which I explain in detail in another video that I'm going to link in the description. It's called Variance Positions in Scala Demystified. You might want to check that out to explain why this kind of error occurs and how you can solve it. So I'm going to use another type argument s, which is a super type of t, and I'm going to use s here for the argument and myList s for the result. So this is how we can solve this error. But the method signature here is really not that important because the myList t is pretty simple to implement. We use a case object that I usually call empty, which extends myList nothing. You remember nothing, this is the bottom of Scala's type system. I have a whole video on nothing here on the channel. And the methods here are pretty straightforward to implement. The head should return nothing, and the only kinds of expressions that can return nothing are throwing exceptions. So I'm going to throw new no such element exception. And again, I'm going to do the same thing for tail, because you cannot really return a list from an empty list. So I'm going to throw new such element exception. I might use a message here, so head of empty list, and something like tail of empty list. All right, so the head and tail are very easy to implement, and prepend to an empty list will return a non-empty list, which is usually implemented in the form of a case class. So I usually use a case class. I usually use the name cons for the ancient term in functional programming to denote a constructor. So the constructor in Lisp-like languages, this would be a non-empty list. So I use cons plus t. And the head and tail are actually passed as arguments, so I override these methods with vals. So I'm going to say override val head, which is a t, and override val tail, which is a myList t. So in one declaration, I override both of these methods with vals, which I also use as constructor arguments, and this extends my list t. And in this case, cons will only need to implement the prepend method, so I just use prepend, and I let the ID complete that for me. And prepending is pretty easy. It just creates a new node, a new list, where the element is the head and the tail is this particular list. So I'm going to use a cons with element and this. However, this method is also present in the empty class, so I'm going to say def prepend, and I'm going to return cons with element and this. So this is basically a very quick implementation of a singly linked list with just 3 methods: head, tail, and prepending. Accessing head is big O of 1 because you just need to fetch the current element of the head of the list. Tail is O1 as well, but figuring out the length of the list or figuring out basically anything else like inserting an element or appending an element takes big O of n. Now, this list, this kind of singly linked list, is pretty easy to implement, and from that my student got to a doubly linked list implementation. So he followed this model and created a doubly linked list implementation, not being aware of the kind of dangers that lie ahead. So this is what I'm about to show you, the difficulty in creating a doubly linked list. So I'm just going to follow this model. I'm going to use a trait. I'm going to call this DL list, and I'm going to make it covariant as well. I'm going to define a method to access the so-called head of the list, which is basically the current pointer of the list, because in a doubly linked list, you might be at any point in the list. So for example, if you have the list 1, 2, 3, 4, 5, you might be at element number 2, and you can traverse either to the previous element or to the next element. So you can traverse in both directions. And so it's worth having a current pointer that I call value. So this value is of type t. This is equivalent to the head of my list thing. And instead of tail, I have now 2 pointers, previous and next. So I'm going to use def prev as a DL list of t and a next, which is a DL list t. And of course, because this is a doubly ended list, we can prepend or append elements to the list. And both of them will have big O of n complexity. So this will be a def, let's call this prepend. I'm actually going to use this exact same definition because we're in the exact same situation. So we have def prepend with another type argument s, which is a supertype of t, so that we can solve the covariant type and contravariant position. And instead of my list, we return a DL list. And append has the exact same signature, so append. And append takes another element and puts it to the other end of the list. Cool, so this is the general trait that describes a doubly linked list. Let's do the empty case, which is pretty straightforward. So I'm going to use an object DL empty, which extends DL list of nothing. And I need to simply implement value prev and next def value, and I'm going to simply throw new no such element exception with, let's say, value of empty list. Because this object is empty, I'm just going to copy this method 3 times, and I'm going to use prev and next. And prev and next are simply going to throw exceptions as well, so previous of empty list and next of empty list. So these are quite straightforward. There is no point in accessing the value or the previous or next pointers of an empty list. Now, prepending and appending are going to be really straightforward in the context of a non-empty class. So I'm going to define a class that I'm going to call cons or DL cons. And I'm going to use a plus t again, and this extends DL list of t. Now, if we follow the same model, this DL cons now should have not 2 but 3 arguments because you have the current value and the previous and next pointers. So I'm going to use a override val value as t, override val next or previous as a DL list of t, and override val next as a DL list T. All right, so this I hope makes sense. And I'm going to use some curly braces because I'm going to implement methods here. And in the presence of this DLCons class, notice I've not made it a case class. I could make it a case class, but I'm going to remove that in a second for reasons that will become apparent shortly. So right now you can feel free to make it a case class. And in the presence of this DLCons class, the append and prepend method on DLEmpty is going to return a DLCons. So I'm going to use def prepend, and this will return a DLCons with the element empty or DLEmpty on the left and DLEmpty on the right. And this will be exactly the same implementation for the append method as well, because appending an element to an empty list will return a non-empty list with a single value, and left and right are both going to be null or empty. All right, so I hope that makes sense. Now, this cons thing, this DLCons, is not really that straightforward to implement the prepend and append methods. So let's say that we have the list 1, 2, 3, so 1, 2, 3 with these dashes here that signify connections, and the empty dashes at the very ends to signify the empty on the left and on the right. And assume that you are at number 2 here. So your value points to the element at number 2. How do you prepend an element to this list? We'd have to find the starting node of the list, say 1, add a new one at the very tip of the left-hand side of this list, and then have its next reference point to the number 1, right? Not quite, because this is a doubly linked list. This existing left end of the list would have to point to the new node as well. So this would have to point to a new node. But because the list as it currently stands points to empty, if you want to update its left reference to a new node, it means you have to replace the node 1 as well. Now, if you replace this part of the list, the node number 2 would have to point to the left onto this new data structure, which means that you'd have to replace the node number 2 again, and the node number 3, and so on and so on. So you'd have to basically replace the entire list without any mutable variables, because these two connections point in both ways. So for example, the node number 1 would have to point to the new node and to the next node that I'm just about to begin creating to create the node number 2. All right. So it turns out that's hard to do in a single operation. We can't have two declared nodes reference each other, because at least one would have to be a forward declaration. So for example, if you want to do a singly linked list, you would have to say val a equals DLCons with, let's say, 5, and then empty or DLEmpty and b, and val b is going to be DLCons with another value, let's say 6, and then the node number a and DLEmpty. Now, this is not applicable, especially in the context of a method. So these values are now members of this object here, DLList playground. So these might be colored a little bit differently, but in a context of a method, these two need to be declared in a single expression. So it turns out we need to do that in a different way. Now, an imperative approach, for example, in Java, would quickly solve this forward declaration problem because we are allowed to mutate references. So for example, we could start with nodes pointing at null, for example, and then change the references to point to the right nodes. So without needing to create nodes every time. But we're not allowed mutation here. So we have our hands basically tied. So enter call by name and lazy vals. So I'm pretty sure you know call by name and lazy values, and if you remember, call by name is the marker fat arrow here attached to a method argument. So if I define a method with an argument which is by name an int, then that means that this argument will not be evaluated inside the method unless it's used, and it will be evaluated as many times as it's used in the method body. So this is called call by name or a by name argument. So we basically defer the evaluation of this argument inside the method body. And again, the lazy concept, if you define a value, let's say a equals 2, if you define that lazy, this a variable here will not take the value 2 unless it's used. And once it's used, the value 2 will be forever bound to this lazy value, so it's not needing to be recomputed every time. Now, I have a video here on call by name. You can find it on the Rock the JVM channel about call by name. This call by name and with the lazy value feature in Scala allows for pretty powerful combinations. So we are going to use these two in conjunction here. So for our use case, this delayed computation allows us to use forward references, meaning that we can define a value and then reference it in the same expression. So I'm going to demonstrate how that would work shortly. So here's a first stab at the non-empty doubly linked list cons thing. So I'm going to remove the case definition because I'm going to pass the prev and the next pointers by name. So I'm going to remove the override val thing, and I'm going to use the by name definition in the sense that this argument will be passed by name when the DLCons class is being constructed, and case classes cannot really have by name arguments. So I'm going to remove the case modifier. So notice that the compiler now is okay with my fat arrow definition here. And the next pointer will also be passed by name because these references will need to be updated later. So in the same style as I showed you earlier, these two-way references will need to be updated at the same time. And we can only do that if we pass them by name in the list that we are about to create. So prev and next are passed by name, and I removed the case modifier here in the DLCons class. I'm also going to use the names p and n so that I can implement the methods prev and next. So I'm going to def prev equals p, but I'm not going to write it as a method, but I'm going to say override lazy value. That is because I want to delay the evaluation of this prev field, and also override lazy val next equals n. So the combination of by name arguments plus the lazy value is called call by need. And we're going to use this technique so that we don't crash the stack or we don't have infinite loops while we evaluate the DLCons instances that we're about to create. So right now I've simply modified the DLCons thing without changing its functionality. Right now, I'm going to show you how to use forward references while doing the prepend and append methods. But if you want to prepend an element to a doubly linked list, you will need to first create a new node at the very end of that list, for example here, as I've demonstrated earlier, and then you need to update all the left references from all the nodes inside the rest of this list. So let's take the smaller problem of updating a node's prev reference. So let's say we have the list 1, 2, 3, and we are pointing at 1 right now. So we are pointing at the node 1, and we want to change this node's left reference to another value. Let's say the node 5. So we want this 5 to point to the node 1, and we want the node 1 to point to this node 5. So we want to create this connection here. So first we need to create another node with the same value 1, whose prev reference now points where we want it, to this node 5. So we need to create yet another node 1 that points to this node 5. Now we then need to update the prev reference of the next node as well. So we need to now update the prev reference for the node number 2. Now think about that. This operation in Java would have been done in 3 steps. So first we would need to create the new node, then the new node dot prev is equal to 5, and then we have new node dot next is the node number 2, and then we would be done. So we need to execute all these 3 operations in a single step, and if we can do that, we've basically made it, because prepend and append is basically relying on that, and we can recursively apply this operation to the rest of the list. Now, strangely enough, this is possible in Scala using call by name and lazy value. So here's how we can do it. We'll define 2 more methods in the main trait. So I'm going to use a method that I'm going to call update Prev, and this update Prev will take a new pointer, a new Prev, which is by name called with a doubly linked list of t. And we return a doubly linked list of t as well. Now, because t is a covariant type, this occurs in contravariant position, so we need to apply this fix as well. So we need to have another type argument, we need to use another type argument s, and we need to return a DL list of s. So this really doesn't change our functionality, it's just for the compiler to be happy. And I'm going to duplicate this method with another method that I'm going to call update next. And this argument is going to be new next. This will operate in a symmetric fashion. So these methods will have the job of updating the left pointers of the entire list, and similarly for update next as well. Now, let me create these methods in the empty class or in the empty object. So I'm going to define update next as being this same empty object, because there's no pointer to update. And so we will need to simply return this empty list. So I'm going to override update Prev as well, and I'm going to return this empty list as well. So note that the method wants to simply replace the next or prev pointers to another reference. And since the empty object doesn't have any, then there's no point in having these do anything. So this is not attaching the new pointer to this list so that we can return a non-empty list. Our job is to simply replace wherever we're currently pointing at to this new reference. And for empty, that doesn't make sense, so we simply return the empty list. Okay, now for the non-empty list, we're going to use lazy vals and we'll exploit the fact that the constructor arguments as well are by name. So I'm going to define update Prev, and be very careful of what you're writing right now. So watch what I'm writing. I'm going to use a val I'm going to call result, and this will be a DL list or DL cons of S. I'm going to simply use DL list. And this will be a new DL cons, where the value of this list is going to be, or the value that I'm currently pointing at is the same value. The previous node is going to be new Prev, because this is the previous node that I'm currently replacing with this new argument. And the next pointer is going to be n.update Prev with, and watch what I'm writing, result. So the result, the node that I'm currently pointing at, the node that I'm currently constructing, will be the previous node of the current next one. So for example, if I have the list 1, let's say, let's start with a dash, 1, 2, 3, 4. And let's say I'm pointing at the node 2. And this node 2 is replacing its previous pointer, which was the node 1, with the node 5. So right now, this will now point to the node 2. Now, once this happens, this new structure over here is going to be the whole previous node of the new node number 3. So this whole data structure, this new result, will be the previous node of what I'm about to construct after that. So this is why I say n.updatePrev result, because I'm going to call the updatePrev method on the node number 3. So I'm going to call the node number 3.updatePrev with this new data structure. And so we'll have a new connection to a new node number 3, and then I'm going to call updatePrev on the next node number 4, and I'm going to create the connection here as well. And after that, we will have the next node update Prev result, which in this case will be empty, and then I'm going to create the empty pointer at the very end of this list. So notice how we can simply replace the end part of a list. However, this code would not compile because the result, the node that I'm currently defining, is part of the expression that defines it. The only way that this could work is to make this a lazy value because it's computed later. And so I'm going to define that as a lazy value and I'm going to return it. All right, so this is how we can create this effect here where we're effectively replacing the left-hand side of a current node. And the same thing I'm going to do with update next because we're going to operate by symmetry. So I'm going to say def update next, and the method definition is auto-completed for me, and I'm going to use a lazy val result as a DL list s, and I'm going to use a new DL cons with the same value. And instead of the previous, I'm going to use the exact same technique. So I'm going to say p.update next result, and I'm going to use the new next, which I receive as argument, and then I'm going to return result. So this is how we can replace the other side of the list as well. And with these two in place, the append and prepend methods are going to be relatively straightforward. So let me go ahead and write them. So I'm going to say def, let's call this append, and append will make use of this same technique. So I'm going to use a lazy val result, which is a DL list s, and I'm going to return a new DL cons. Now, if I want to append a value to a non-empty list, I need to stay at the same value, so I'm going to use the same value here. Now, the left side of this list is going to be the previous node dot update next result, because I'm replacing the current list with a new list, and so the previous pointer needs to update its next reference to me, the me that I'm building. And the other expression here for the tail, I'm going to simply say tail, or the next dot append element. So this is the recursive call, and I'm also going to need to update the pointers as well. So I'm going to say update prev result. So notice that we don't have one, but two forward references to the result node that I'm currently building. And just to illustrate how this would work, so let's say we have the list 1, 2, and 3, and we want to append the node 4 to the list that we're pointing at the element 2. So first of all, we need to create another node with the same value. So I'm going to create a new value, 2, and the previous node to this list that I'm currently building is the previous node p, which has the value 1, update next result. So I need to have 1 and then the connection to here. And we already demonstrated how that would work. And then a recursive call to tail.append elements. So we have 3 and 4. And then I also need to update the previous reference to that to the node that I'm currently building, so that the end result is going to be the list 1, 2, 3, 4 with the pointer pointing at 2. So I hope that makes sense. And I'm going to return result as well. And for prepend, we're going to operate in a symmetric fashion. So I'm going to define prepend, and I'm going to use a lazy val result as a DL list s as a new DL cons with value. And then I'm going to use p.prepend element dot update next result. All right, so where in the first case I did the next pointer append element, here I'm going to say previous.prepend element update next result, and then n.update prev result. And then I'm going to simply return the result that I'm currently building. And if you want, you can pause the video and prove that this prepend operates in a symmetric fashion to append. And this is basically it. This is how we can use a forward reference with lazy vals and call by name to implement a immutable doubly linked list. Let's go ahead and test this out. So I'm going to simply define a main method, and I'm going to define a small list as dlEmpty.prepend1 append 2, prepend 3, append 4. So I'm prepending 1, appending 2, prepending 3, and append 4. So in this list that I'm building here, I should end up with the list prepending 1, appending 2, prepending 3, so we have 3 here, and appending 4. So 3, 1, 2, 4 with the node pointing at 1, because this is the first element that I've added to the list. So if I print line list.value, I should get the value 1. If I print line list next value, I should get the number 2. If I print line Let's also test that the pointers work correctly both ways. So I'm going to say list next prev equals list. So this should return true. I will print line list prev value, and this will be the number 3 because this is the node to the left of the main node of the list. And let's say print line list prev next equals list. So we're testing the pointers both ways in the other side as well. So this should return true as well. If I print line list next value, this will be 4. And let's also test twice the traversal. So I'm going to say list next prev equals list, and this should return true. So right now I've written almost 100 lines of code. Hopefully it compiles and hopefully it runs. So let me go ahead and run this application. A few seconds for the compiler to run, and lo and behold, I have an output. So we have 1, 2 true, 3 true, 4 true. So the code works correctly. So I hope you enjoyed this video with a pretty interesting technique for defining data structures with forward declarations. If you like this video, go ahead and click the like button for me and subscribe to the channel for more videos like this, and follow me on Twitter and LinkedIn for updates on upcoming material. As always, I'm dying for feedback, so leave your comments. I read every single one, and check out the Rock the JVM website where we have tons of videos and lessons like this. Until next time, I'm Daniel, signing off.